Many phenomena in the world are oscillatory in nature. Think about, say, the tides or this amount of sunlight over the day or waves in water. So it would be nice to be able to describe these sorts of phenomena. In other words, describe oscillations. Um, just to have a concrete example of a simple system that produces oscillatory behavior, let's suppose that we have a mass, a weight hanging from a spring like this, and we give it a push so that it moves up and down from its central point where it was hanging at rest. If you graphed the height of this weight above the tabletop, so you might have your horizontal axis be time and your vertical axis be height, and this will be a function of time. So if you graphed this, you can imagine that it would look something like this. It sort of depends on how far up and down it goes and how quickly it moves through the cycle, but it's going to oscillate between some minimum and some maximum value. And if you look at this graph, it looks like this might be a transformed sine graph. Any function that is just a transformed sine graph is called sinusoidal. Okay, so this function f of t is a sinusoidal function. And well, if you ask a physicist to analyze this situation with a mass hanging from a spring, they will find that this situation does actually produce a transformed sine graph for this height function. Physicists call this kind of motion with something bobbing up and down so that it produces a sine graph, they call this harmonic motion for historical reasons. And since it's a transformed sine graph, we can use what we know about sine graphs to come up with a formula for this function f of t. So the important things to notice about this sine graph is, first of all, where the middle of its oscillation is. So let's call that B. I'm going to try to use the same names as the book. So B this is the middle of the oscillation. That's often called the mean of the oscillation. And for a regular sine graph, the middle is at 0. Well, this middle is at B, so this means that this is going to be a vertical shift. We're going to have to do some kind of vertical shift to get the middle of the oscillation from 0 up to B. The distance from the middle of the oscillation to the top, that's what we call the amplitude. So A is the amplitude. And for an untransformed sine graph, that would be 1. But, you know, your mass bobbing up and down probably won't go up and down exactly 1 unit. And so you're going to have some sort of vertical stretch to make the amplitude be what you observe in the spring. Next, the length of time that it takes to go through one cycle, that would be this distance. That's the period. And we found that for a sine function, the period is related to this number k by the formula k equals 2 pi over the period. And the way that k shows up in formula, it shows up as a multiple inside your sine function, and that causes a horizontal compression. Okay, so with these transformations, the formula that we get for f of t is a times sine of k times t plus b. And the b has to show up here so that it performs a vertical shift. A has to show up here so that it performs a vertical stretch, and k has to show up multiplying inside so that it performs a horizontal compression. Notice that if A is negative, then we also have a vertical flip that happens. This graph of sine initially goes up. If your harmonic motion is initially going down, then you would need to do a vertical flip. Okay, so this is our general formula for a sinusoidal function. Well, almost general, as we'll see a little later. So this is a sinusoidal function. And there are a couple of notes I want to make about this formula. So first was, so a could be negative. Second note that I want to make about this formula is if your sinusoidal graph, if you start at the top or the bottom of a cycle, well, you can't use sine because sine always starts at the middle of the cycle, going up if it's unflipped and going down if you flipped it vertically. So if you need to start at the top or the bottom of a cycle, use cosine instead, because it starts at the top of the cycle. So if you need to start at the top of a cycle, use cosine. If you need to start at the bottom of a cycle, use the flipped cosine. Okay, so with all of this in mind, let's actually use this to describe some oscillations. So here's our first example. Let's say we have a mass hanging from a spring that starts 3 centimeters above the tabletop, and it reaches its high point at 9 centimeters above the tabletop after 1/10 of a second. So let's find a sinusoidal model h of t for the height of the mass after t seconds. So let's see. All of these numbers are kind of a lot to digest, so let's just take it piece by piece. So we're going from a minimum of 3 centimeters to a maximum of 9 centimeters. So that's going to be like this, 3 centimeters up to 9 centimeters. The middle is exactly halfway in between, so that's going to be at a height of 6 centimeters. And so the distance from the middle to the top and the middle to the bottom looks like it's going to be 3 centimeters. And so that's going to be our amplitude. So our amplitude is 3. Also, the middle of our oscillation is 6 centimeters. And so that's going to be the mean, B. So that's our vertical shift. Okay, finally, looking at the amount of time it takes. So it takes 1/10 of a second to go from the bottom to top. So bottom to the top is 1/10 of a second. So, well, that means it's going to take another 1/10 of a second to go from the top to the bottom. And so the total length of a cycle is going to be 2/10 of a second, or 1/5 of a second. So that's the period. So period is 1/5. And so our value k is 2 pi divided by the period. So 2 pi times 1/5. And then simplify your fraction by multiplying numerator and denominator by 5. And you get 10 pi for the value of k. So our function h of t, the amplitude is going to be 3. We need to decide which trig function to use, but inside the trig function, we're going to have 10 pi times t, and then plus our value for b, which was 6. Okay, so this oscillation, it looks like it starts at its low point, and so we can't use sine. Using sine, we would start in the middle of an oscillation, in the middle. Since we're starting at a low point, we have to use cosine, but cosine starts at the top. To make it start at the bottom, we need a minus sign in front to flip the starting point from the top down to the bottom. So here's our sinusoidal function to describe the height of the mass hanging from the spring. Okay, let's look at another example. So the temperature of a lake varies roughly sinusoidally over the course of the day. The lowest temperature is at 54 degrees Fahrenheit at 6 a.m. Highest temperature is 70 degrees at 6 p.m. Find a sinusoidal function, capital T of little t, for the temperature t hours after midnight. All right, so let's do the same sort of analysis. We are going from 54 degrees up to 70 degrees. That's going to look like this, from 54 up to 70. And the midpoint, you might need to calculate the midpoint by just averaging these two temperatures, but you're going to get, I guess, 62 degrees. Okay, that means 62 is going to be our value for our mean. The amplitude is the distance from the middle to the top and the middle to the bottom, and that's 8 degrees in this case. So that's our amplitude. Looking at the times, going from 6 a.m. to 6 p.m., that's from the bottom to the top. So that's 12 hours. And so one complete cycle is twice that. So that's 24 hours. No surprise that it's one entire day. And that means our value for k is 2 pi over 24. So that's pi over 12. Okay. And then finally, we need to choose which trig function we're going to use, sine or cosine. And if we need to flip it, we have to decide where in the cycle it starts. So we're measuring time starting at midnight. And so we need to figure out at midnight, what is the temperature? So let's see, at 6 p.m. it's 70 degrees. At 6 a.m. it's 54 degrees. So it looks like halfway in between is midnight, and it's going to be, the temperature is going to be at the middle. So we're going to use a sine function, not cosine, but it's also decreasing, not increasing. So since we are starting at the middle, we're going to use sine. And since we're decreasing and not increasing at our starting point, we're going to need a vertical flip. Okay, so our function, capital T of little t, is our amplitude, which is 8, but also with a minus sign to make that vertical flip happen, times sine of, and then our value for k, which is pi over 12 times t, plus our value for the mean, which was 62. All right. Now that we have this function, we could do all sorts of things with it, like forecast what the temperature of the lake would be at any particular time of the day.